Try to imagine a square, its four sides fitting neatly within the familiar two dimensions of space. Now, from each corner of that square, you draw a straight line perpendicular to it, piercing out of the plane, stepping into the third dimension, and a cube appears. But we do not stop there. From the 8 vertices of that cube, each vertex extends a new line this time, perpendicular to all the lines before it, thrusting straight into a direction the human eye cannot see. The mind can scarcely grasp. What is created is called a hypercube, also known as a tesseract, an object of the 4th spatial dimension. Such multi-dimensional shapes are almost unimaginable to the human imagination. And yet, if you could imagine them, then in the mid-19th century, in Victorian England, people believed the reward for you would be immense. For many intellectuals of that era, the 4th dimension was not merely a mathematical concept, but a doorway to the spiritual world, a sacred realm where science, philosophy, and theology converged. The origins of this idea began in science. Mathematicians like Bernhard Riemann broke the framework of classical geometry, where the sum of the 3 angles of a triangle is always 180 degrees and parallel lines never meet. He opened up a new kind of geometry, the geometry of curved and multidimensional spaces. And from that rigorous foundation, the rich imagination of the Victorian age quickly transformed the 4th dimension into an almost mystical land, where people hoped to find a connection to higher layers of existence. But not everyone saw light there. For H.P. Lovecraft, the New England writer born at the end of that century, higher dimensions carried no sacred color at all. They brought only horror. In The Dreams in the Witch House, the character Walter Gilman, a student of physics and mathematics, discovers that the room he rents has warped dimensions, deviating from familiar reality. Each night, dreams pull him deeper into multidimensional planes, where ancient gods and beings beyond human understanding dwell. The fear Lovecraft touched is a very primal fear, the fear of the unknown, the fear before the true scale of the universe, and before what might exist just beyond the edge of our awareness. And yet, not everyone turned away from that abyss. Some people, perhaps brave, or perhaps reckless, chose to look straight into the darkness. Over the past century, scientists have begun to ask in earnest, do those hidden dimensions truly exist? And today's answer, strangely, is both close to Lovecraft and completely different. It may be true that higher dimensions exist, but not as supernatural realms looming over us. Instead, from a completely opposite viewpoint, our entire universe may be only a thin 2-dimensional membrane, floating in a higher dimensional space. Matter, gravity, even space-time itself may be the result of reducing the number of dimensions, not increasing them. And that story about how many dimensions the universe hides and how fragile our reality may be will lead us back to a familiar name. Albert Einstein was not a late-blooming genius. Historical records show he was a prodigy very early on, especially in physics. Einstein's childhood was intertwined with electricity and magnetism, 2 invisible but powerful forces, because his father's and uncle's company manufactured electrical equipment. Being exposed to science from a young age left a deep imprint, becoming the foundation for his later intellectual revolutions. That story is a clear testament to the power of early curiosity, a small spark that can light up a lifetime of discovery. And that spirit is exactly what KiwiCo aims for. KiwiCo offers monthly hands-on projects designed for every age and interest, from little kids discovering the world for the first time, to teenagers and even adults who want to try their hand at science, engineering, or art. Our producer's family had a wonderful time with Kiwi Crate, the subscription box for children ages 6 to 9. They built a mini planetarium together, assembled constellations, designed a sky map, and watched how the Earth and Moon orbit the Sun. The excitement of opening the box, along with the reusability of the models, made the experience not something that happened once, but something that repeated again and again. If you want to spark a similar passion for the young scientists and engineers in your life, use the code History of the Universe to get 50% off your first KiwiCo crate. Or visit kiwico.com, History of the Universe. And now, with curiosity awakened, we can truly begin to ask, if the universe has more dimensions than what we see, then where are they hiding? And what do they say about the deepest nature of reality? Perhaps Walter Gilman should not have studied so obsessively. Non-Euclidean geometry and quantum physics are enough to stretch any brain to its limit, and when people mix them with folklore, then try to follow the faint traces of a multi-dimensional reality behind the familiar world, it is hard to expect the mind to keep its balance. Just like the warped room Gilman discovers in his dreams, the journey to find answers about higher dimensions and lower dimensions as well is a strange, winding, and full of surprises path. And the paradox is that journey does not begin at the edge of the universe, nor does it arise from the quantum nature of space-time. It begins in a place that seems very earthly, the effort to build more efficient steam engines. Death is nothing at all. People say, Napoleon once uttered, but to live in defeat and lose glory is like dying every day. On October 15th, Itembabe Ishiwu, Napoleon Bonaparte, the former emperor of France, who had once shaken nearly half of Europe, set foot on the final territory of his life, the small island of Seyo. Helena. This was his second exile, and also the last prison he would never leave. It is said that in his final years, on that isolated rocky outcrop in the middle of the Atlantic, Napoleon still demanded that his attendants wear uniforms, and that women wear evening gowns. The defeat at Waterloo, only a few months earlier, remained a wound that never healed. The conquest had ended. No more victorious armies. No more triumphal arches. What Napoleon left behind was a fragile monarchy restored in France, a new regime that had no tolerance for those who had once been connected to the exiled emperor. Among them was a young military engineer, Sadi Carnot, born in 1796. Sadi was the son of Lazare Carnot, an outstanding mathematician and also a military commander of the French Revolutionary Army, one of the few who had skillfully survived the political storm during Napoleon's rise. But that good fortune did not smile on Sadi. Though he still kept a position in the army, he was repeatedly passed over for promotion because of his family's connection to the deposed emperor. In the end, Carnot accepted a position that was almost symbolic, along with a pay cut, in exchange for something far more valuable, time to pursue his intellectual reflections. Those reflections would completely change how we understand reality. Carnot believed that one reason France had been defeated lay in the inefficiency of its engines. If one could understand and describe an ideal machine, a perfect engine, then national power might have been different. From that idea, he set out to describe the optimal engine in mathematical terms. The result was a treatise titled Reflections on the Motive Power of Fire. Sadly, Carnot died in 1832, at only 36 years old, and his work went almost unnoticed throughout his lifetime. But the history of science often has such slow turns. Many decades later, that slim book fell into the hands of Rudolf Clausius, a German physicist and mathematician. Something in Carnot's thinking sparked Clausius's sharp imagination, and in 1850, Clausius stated a principle that would become a foundation of modern physics, the second law of thermodynamics. 15 years later, he introduced a new concept, a word that would haunt science, philosophy, and cosmology for many centuries to come: entropy. At the time, Clausius could not know what he had opened. At the core of thermodynamics are three foundational laws. The first law affirms an almost obvious truth: energy cannot create itself or destroy itself. It can only transform from one form into another. The second law, recognized by Clausius, says that the entropy of an isolated system never decreases. The consequence is that heat never spontaneously flows from a cold object to a hot one. Order tends to dissolve into chaos, and the third law states that as a system approaches absolute zero, its entropy approaches a constant, implying that no physical system can truly reach a temperature of zero. At the center of the second and third laws is that new and haunting concept entropy, a quantity born from steam engines, but which ultimately became the key to opening the deepest questions about time, order, and the structure of the universe itself, and, as we will see, dimensions beyond human intuition. For many centuries, beginning in Newton's time, scientists believed that heat was a kind of invisible particle, some sort of substance that flowed from one object to another, like water poured from one vessel into another. But Rudolf Clausius disagreed. To him, the core issue was not how energy moves, but how energy is used. Clausius recognized a subtle but revolutionary truth: although energy is never created or destroyed, not all energy is useful. When a piston drives an engine, some energy becomes useful motion, but another part disappears as friction, heating the contacting surfaces without producing work. When a flame is used for cooking, only part of the heat cooks the food. The rest is lost as light, smoke, and waste heat spreading uselessly into the surrounding air. From those seemingly obvious observations, Clausius reached a bold conclusion. Heat is not only something that is transferred, but also something whose quality can change. There is heat that can do work, and heat that cannot. To track this portion of energy that has become useless, he named it entropy, the three laws of thermodynamics. Therefore, proved extraordinarily effective. They explained experiments, accurately predicted the behavior of machines and matter, and quickly became the foundation of 19th century physics. But no matter how successful they were, they still carried a certain mystery. Where did these laws come from? What did they reflect? More deeply, about the nature of the world. As the pioneering generation Sadi Carnot and Clausius passed away one by one, that task was handed to the next generation, those who did not merely accept the laws, but wanted to understand why they were true. And it was they who discovered that behind those dry equations lay connections far deeper than anything their predecessors had imagined. It is great to command millions of people in national projects, or to lead 100,000 soldiers to victory, a scientist once wrote, but greater still is to discover foundational truths in a humble room, with simple means truths that will remain the groundwork of human knowledge when the memory of battles exists only in the archives of historians. That spirit was embodied most clearly in Ludwig Boltzmann, an Austrian physicist born in 1844, more than a decade after Carnot's death, and more than 20 years after Napoleon had permanently become a name in history books on the island of Saint Helena. Boltzmann was a scientist in the modern sense. He sensed that the three laws of thermodynamics were not merely separate experimental rules, but expressions of something deeper, tied to the microscopic structure of matter. At that time, scientists were only beginning to classify and understand elements like hydrogen and oxygen, and their properties. Many suspected that matter was made of basic units atoms, but direct evidence was still lacking. What made Boltzmann bold was that he dared to connect this atomic hypothesis with the laws of thermodynamics that were already widely accepted. In his vision, gases and liquids were not smooth, continuous blocks, but vast crowds of countless tiny particles, always moving, colliding, and interacting. Boltzmann believed that if we understood the behavior of each of those tiny particles, then the large-scale laws, temperature, pressure, entropy would naturally emerge as statistical consequences. And he was right. Boltzmann's revolution began with the very concept of entropy. In 1877, Boltzmann proposed a completely new definition of entropy, no longer based on uniform blocks of matter, but on the number of possible arrangements of the microscopic particles inside a system. For him, entropy did not measure disorder in a vague sense. but measured how many different microscopic configurations could produce the same observable large-scale state. To picture this, imagine something very ordinary: cleaning the kitchen. You wash the dishes and stack them neatly in the cupboard. You take out the trash, throw away moldy food in the refrigerator. You even scrub away the grime that has built up for a long time behind the sink. After hours of work, you step back and admire the result: a perfect kitchen. Everything is in its proper place. According to Boltzmann, this is a very low entropy state. Cleanliness is the macroscopic quantity you can observe and measure. But to achieve that state, there is only one unique arrangement of every plate, every piece of trash, every surface. In Boltzmann's language, there is only one microstate that leads to the macrostate: a perfectly clean kitchen. Now fast forward 24 hours. You cook, do a quick tidy up, open the refrigerator at midnight looking for a snack. After just one day, the kitchen is no longer perfect. A cup is still in the sink. A breadcrumb lies on the edge of the counter. A ring of coffee is stamped onto the wooden tabletop. The kitchen is now in a higher entropy state. Slightly messy is the new macrostate. And what matters is there are countless different ways for the kitchen to become slightly messy like that. One small detail out of place is enough, but that detail could be anything. There are more ways to be messy than to be tidy. And it is precisely the enormous difference between the number of those microstates that makes entropy always tend to increase, not because some mysterious force compels the universe, but because of pure statistics. And from here, the link between entropy and disorder gradually becomes clear. Strictly speaking, entropy is not messiness in the everyday sense, but a measure of the number of microstates, the number of arrangements at the microscopic level that can lead to the same thermodynamic state we observe, like temperature or pressure. However, in practice, the two concepts almost run in parallel. The higher the entropy, the more microstates there are, and the more the system tends to look messier. This realization, the deep connection between the invisible tiny motions of particles and the big laws governing the world, gave birth to an entirely new field, statistical mechanics. Today, we understand that all of thermodynamics actually arises from statistical mechanics, especially after the existence of atoms was demonstrated by Albert Einstein in 1905. Laws, once derived from steam engines and laboratory experiments, turned out to be natural consequences of probability and large numbers. Take temperature as an example. In a gas, temperature is not an abstract quantity, but the average kinetic energy of the particles. The hotter the gas, the faster the molecules move. When you put your hand into a stream of hot air, billions of tiny particles strike your skin every second, transferring their energy to your body. That burning sensation is not mystical, it is statistics happening on your skin. And this is the core power of statistical mechanics. We do not need to know every microscopic detail. No one has to track the position and momentum of every air molecule to determine the temperature of a room. Instead, we work with probabilities, with averages, with microstates and distributions. That is why statistics becomes the foundational language of this field. However, the 19th century pioneers of thermodynamics and statistical mechanics did not yet open the door to other dimensions. They were building a mathematical toolkit, abstract concepts, but extraordinarily powerful. Any object that has heat can be described by entropy, and entropy can be traced back to microscopic motion. In the decades that followed, those very tools would be applied to places no one expected, to objects that seem incapable of having heat, incapable of having microscopic structure in the familiar sense. Black holes. And in the journey to explore the thermodynamics of black holes, the first signs appeared, the signs that something was very, very wrong with the universe. In Lovecraft's story, Walter Gilman gradually loses his anchor of reason. His dreams go far beyond all standards of sanity. Nourished by equations pointing to hazy regions beyond the familiar 3 dimensions of space, Gilman believes he has stepped into another world, a higher dimensional space, where matter and gravity follow completely alien laws. Lovecraft writes, those abysses were not empty, but crowded with slanting masses of matter beyond description. Of alien, Iwe, everything he saw exuded a threatening and unnameable horror. Fortunately, on our journey to the most extreme place in the universe, the logical endpoint of thermodynamics, we will not be alone. We have a guide, someone accustomed to facing paradoxes that seem demonic. I see the world as a product of God. Jacob Bekenstein was a man of deep faith. But for him, that faith did not conflict with science at all. On the contrary, he saw the discovery of the universe's deep laws as a form of worship. The more one understands nature, he believed, the closer humanity comes to understanding the Creator. Bekenstein was not alone on that tightrope. Newton was once a devout Christian believer. Georges Lemaitre, the father of the Big Bang Theory, was a Catholic priest. In that tradition, Bekenstein stepped into the borderlands of modern physics with both humility and boldness. And then, in the early 1972, his research led straight to an entity that bore no resemblance to the sacred, something closer to the embodiment of absolute destruction. Black holes, objects where space and time collapse into themselves, where entropy, temperature, and the second law of thermodynamics collide head-on with gravity and relativity. It is here, in the deepest darkness of the universe, that dimensions, entropy, and the nature of reality begin to merge and reveal that our understanding of the universe may have only touched the surface. There is no monster in the universe more terrifying than a black hole, nor does any greater power of destruction exist than they do. No planet survives if it comes too close. No star can resist. And in some extreme cases, even gigantic galaxies must bend and warp under their influence. At first glance, black holes seem to have nothing to do with thermodynamics, statistical mechanics, or the hidden dimensions we have been tracing. They first appeared not in a laboratory, but buried deep in the equations of Einstein's general theory of relativity. In the words of Nobel Prize-winning physicist Subrahmanyan Chandrasekhar, black holes are the most perfect macroscopic objects in the universe. Their structure needs no atoms, molecules, or chemical forces, only space and time. And yet that very perfection is what makes black holes the biggest headache of modern physics. They do not deliver easy answers. Instead, they open two profound mysteries tied to the nature of reality. The first mystery lies at the singularity, at the center of a black hole, where relativity predicts that density becomes infinite. But infinity cannot exist in any complete physical theory. The appearance of a singularity is a quiet but decisive declaration that general relativity is not the final picture. There must be a deeper, more fundamental theory to describe what truly happens there. Ironically, that singularity is forever out of reach. It is imprisoned behind a one-way boundary, the event horizon. You can cross that horizon if you are reckless enough. But like the unfortunate characters in Lovecraft stories, you will never be able to return to tell the universe what you saw. And it is that event horizon that brings us to the second mystery, no less haunting. A black hole is the only place in the universe you can go into, but cannot come out of. A door that opens in only one direction. What does that mean for information? For physics? For the nature of reality? Is the event horizon truly a one-way road, or is there something else waiting behind that dark curtain? Questions like these drove Jacob Bekenstein. The singularity was a colossal problem. But for him, the event horizon was even more mysterious, because at least it is something the outside universe can observe. And then, in 1973, Bekenstein discovered something both strangely simple and unbelievably deep. For all their reputation as cosmic monsters, black holes are extremely simple. From the outside, they display only three measurable properties: mass, electric charge, angular momentum, also known as spin. It does not matter what falls inside. Stars, gas, cosmic dust, planets, moons, comets, or even pure information. Everything disappears past the event horizon. The only thing the outside universe can still see is those three numbers. Even if you create two black holes from two completely different sources, one from the collapse of stars and nebulae, one from a vast information structure, such as a number extending to infinity if they have the same mass, charge, and spin, no measurement can distinguish them. Bekenstein called this idea the no-hair theorem. In other words, black holes do not care about details. Every complex feature is shaved away. His mentor, John Wheeler, loved that phrasing. Richard Feynman thought it was distasteful. But despite controversy, the name remained and became etched into the history of physics. This informational nakedness led some theorists to suggest that black holes might be regions with zero entropy, places that contain no information. But Bekenstein quickly realized that could not be true. If black holes had no entropy, then throwing matter into them would erase information, something absolutely forbidden in quantum mechanics. Information cannot simply vanish. So Bekenstein reached a bold conclusion. Black holes must have entropy. But the question is, how much? His answer was even stranger than the black holes themselves. Bekenstein proposed that a black hole's entropy is proportional to its surface area, specifically the area of the event horizon, not the volume. The larger the black hole, the wider the event horizon, the higher the entropy. From that, he made a shocking statement. Later known as the second law of black hole thermodynamics, the area of the event horizon never decreases. In other words, the event horizon never shrinks. A statement that sounds purely geometric, but contains profound consequences for entropy, information, and perhaps dimensions beyond human imagination. This idea was, in fact, a direct parallel to the second law of thermodynamics, the law that states that in a closed system, entropy never decreases. And because Bekenstein assumed that a black hole's surface area is proportional to its entropy, a new second law for black holes almost automatically emerged as a logical consequence. At that time, it was still only a hypothesis, a bold conjecture, built on sharp physical intuition, but without solid evidence. It was compelling. It was reasonable, but still an untested guess. And then Stephen Hawking appeared. Unlike Bekenstein, Hawking was not a man of religious faith. He once said God is a name people give to the reason why we are here. But I think that reason is the laws of physics, not some being with whom one can have a personal relationship. Even so, there is no record that this difference in worldview ever caused tension between the two men. Hawking's only disagreement with Bekenstein was in physics. Hawking believed that Bekenstein's ideas, interesting and potentially profound as they were full of errors. His central argument was clear. Black holes cannot have entropy because they do not emit radiation. No radiation, no heat, and if there is no heat, then applying thermodynamic concepts, entropy, temperature is completely inappropriate. With his usual confidence, Hawking set out to prove Bekenstein wrong, but in the process, he discovered something no one expected. By carefully tracking the evolution of the event horizon from the moment a black hole forms, Hawking realized that this one-way boundary interacts with the surrounding spacetime in extraordinarily strange ways. Through a subtle effect of quantum mechanics, particle-antiparticle pairs can appear near the event horizon, and in some cases, one particle can escape outward. The shocking conclusion: black holes are not completely black. They emit an extremely tiny amount of radiation, so slowly that it is almost impossible to notice. Hawking's 1974 publication was like a bomb detonating in the foundations of theoretical physics. For a long time, scientists had suspected that black holes concealed something more than what Einstein had described. but no one predicted that they would radiate. This kind of radiation later came to be called Hawking radiation. With a strange feature, the smaller a black hole is, the stronger the radiation, while supermassive black holes evaporate extremely slowly. But the story did not end there, because the combination of Hawking radiation and Bekenstein's original insight about black hole entropy created one of the deepest and most persistent paradoxes of modern science, the black hole information paradox. First, Bekenstein's second law of black hole thermodynamics, in its original form, is no longer absolutely true. The area of the event horizon does not always increase. If a black hole is left isolated, with no matter falling in, it will gradually shrink, losing mass over time due to Hawking radiation. However, Bekenstein was right about the essential point: black holes truly do have entropy. If black holes did not emit radiation, everything would be simple. Information would not be destroyed, it would merely be hidden forever behind the event horizon. But black holes do not last forever. They evaporate and eventually disappear completely. So what happens to the information that made that black hole? Hawking pointed out that Hawking radiation carries no information. His calculations showed it to be completely random, like the radiation from an ideal black body. If you track every photon, every particle emitted from a decaying black hole, you cannot infer what was originally inside the black hole. This means Bekenstein's no-hair theorem still holds. Once a black hole swallows something, information about that thing cannot be accessed from the outside. But then the black hole disappears. And if information does not escape with the radiation, where did it go? This is the heart of the black hole information paradox, the possibility that black holes can destroy information. Something absolutely forbidden in quantum mechanics. Information is never allowed to be destroyed. So Bekenstein and Hawking cannot both be right in the simple way. Either Hawking radiation must carry information, and Hawking was wrong about its nature, or black holes are not truly bald the way we think, and Bekenstein missed something. This paradox has fascinated physicists from the early 1970s to the present day, and it has also revealed strange clues about the dimensional nature of reality. Our story began with Carnot. With the ambition to improve steam engines, Clausius continued, building the laws of thermodynamics and naming entropy. Half a century later, Boltzmann discovered that all of thermodynamics arises from an even deeper layer of physics. And now black holes, the most extreme objects in the universe, display thermodynamic-like properties: entropy, radiation, temperature. If thermodynamics comes from deeper physics, then it is very possible that black holes do as well. But what does this connection really say about the ultimate nature of reality? The answer may not lie deep in the core of a black hole, but right on its surface, on the event horizon itself. And while Bekenstein and Hawking were grappling with these cosmic monsters, a completely different line of research was also quietly developing, unrelated to astronomy. Not about black holes, but emerging from light and lasers. It was there that physicists began to realize that under certain special conditions, the universe's three spatial dimensions are not always necessary. Sometimes, 2 dimensions are enough. What makes students shake their heads is that cold, haunting hypothesis that a human being, if possessing mathematical knowledge deep enough, an understanding almost beyond all human capability, could deliberately step away from Earth to appear at any other celestial body. As long as that body lies at one of countless special points in the model of the universe. In this view, a being from any region of 3-dimensional space, in principle, could fully exist in the 4th dimension. In Lovecraft's stories, Walter Gilman's dreams gradually take over his mind, pulling him away from familiar reality and carrying him into strange regions of space. As if existing outside our world, the boundary between waking and dreaming begins to dissolve, and with it Gilman's mental stability. And from here, an unavoidable question arises: if Gilman could, though only in fiction, cross from our 3-dimensional reality into higher dimensional spaces and suffer the consequences, then can we, by the path of modern theoretical physics, do something similar, if we could catch even a glimpse of worlds beyond dimension, what would that say about our own universe? To begin approaching this strange question, we must return to the early 20th century. With a teenage boy standing between battle lines, Denis Gabor was born in Észak-Kilencszáz in Budapest, Hungary. When he was very young, he served in the artillery of the Austro-Hungarian army during World War I, taking part in battles against Italy. After the war, Gabor continued his studies in Germany and quickly proved outstanding in electronics. But in the early 1932s, the political storm arrived. Gabor had Jewish blood, and although he had served in the army, that meant nothing to the rising Nazi regime. In 1933, he was forced to leave his homeland and accepted an invitation to work in England. Yet amid those violent upheavals, his passion for electrons, light, and lasers never cooled. And it was in England that Gabor made a revolutionary discovery: holography. Normally, when you take a photograph, most information is lost. Imagine you are standing before a majestic mountain range. You can move, change your viewpoint, observe details in three-dimensional space. But the moment you raise your phone and take a photo, all that freedom disappears. The photograph locks you into a single viewpoint. No matter how you walk around the framed picture on the wall, you only see its back. You never see the backside of the mountain. In other words, traditional photography destroys spatial information. Gabor found another way. By letting beams of light interfere in a controlled way, he realized he could encode the full three-dimensional information of an object onto a two-dimensional surface. A hologram does not just record an image, it records how light is reflected and propagates from the object. When the appropriate light is shone back, the original light pattern is reconstructed, and with it, a complete three-dimensional illusion of the object. With a true hologram, you can change your viewpoint, walk around the image, observe different details, almost no different from the real object. Although this invention was published in 1947, it took decades to be fully recognized. Only in 1971 did Denis Gabor receive the Nobel Prize in Physics. In the public eye, holography mostly existed as an element of science fiction, for example. Princess Leia's distress message in Star Wars. The holograms, commonly seen in everyday life, are actually just embossed plastic prints, not carrying the physical essence of a true hologram. But physicists saw something deeper, because under special conditions, a three-dimensional world can be compressed into two dimensions without losing any information at all. And at the center of this conceptual revolution was another person, also swept into the vortex of World War II. I could smell the war coming. He once said, "I thought I would be safer working full-time for the war effort, and, moreover, I believed I could contribute more that way." That person was Claude Shannon. He joined Bell Labs in 1941. Instead of holding a gun on the battlefield, Shannon thought about mathematics so constantly that he wrote equations on napkins during meals. A colleague once described him as intellectually irritating a mind too sharp, too fast compared to those around him. During the war, Shannon worked in cryptography and even met Alan Turing many times. But his greatest work appeared only after Berlin fell. In 1948, Shannon published a foundational paper on the nature of information and communication. In it, he introduced a way to measure the amount of information needed to describe the possible states of an unknown system. What astonished Shannon was that the formula he found had a form almost identical to Boltzmann's entropy formula in thermodynamics. And so, he borrowed the term itself. From here, entropy was no longer only a concept of heat and energy, but became a measure of information. A bridge had been built between thermodynamics, statistical mechanics, light, information, and gradually, between the number of dimensions of the universe. Claude Shannon's work was not only a milestone in information theory and computer science, but very quickly spread deeply into physics as well, because at the deepest level, What physics cares about is nothing other than the state of a system. In the language of physics, the state of a system is the complete list of all information needed to describe it, the positions, momenta, and energies of all particles within a given volume. If you possess that list, together with the laws of physics, then, in principle, you can predict the system's future with perfect accuracy. Sometimes, this list is short and easy to manage. For example, to calculate the trajectory of a projectile, we only need to know its initial position and momentum. But in many other cases, that list becomes so enormous that it cannot be handled directly. Think of a gas cylinder. The number of molecules inside it can far exceed the total number of stars in the observable universe. Tracking each molecule with its own position and velocity is completely meaningless, and it is precisely here that macroscopic quantities temperature, pressure, density become our salvation. Through statistical mechanics, we do not need to know every microscopic detail. We only need averages to grasp the overall behavior of the system. But the core point is this information is the heart of predictive power in physics. When you know enough information about a system, you can say what will happen next. Quantum mechanics changes the picture slightly by replacing certain predictions with probabilities, but the basic game remains the same. Track information, describe the state, predict the future. That is why Shannon's choice of the word entropy for his measure of information was not accidental. In thermodynamic systems, there is a clear mathematical relationship between entropy and the amount of information needed to describe the system. In fact, Boltzmann's and Shannon's formulas, though coming from two completely different fields, have an astonishingly almost identical form. This deep similarity led John Wheeler, Jacob Bekenstein's mentor and a giant of theoretical physics, to a famous statement, "It from bit," the idea that perhaps information, not matter or energy, is the deepest foundation of reality. Even if we do not go that far, the relationship between these forms of entropy still carries an extremely important consequence whenever a system in nature obeys the laws of thermodynamics. We can assign it a definite information content, whether the system is classical or quantum. And as Bekenstein found and Hawking confirmed, black holes clearly behave like genuine thermodynamic systems. It was precisely the question of information falling into a black hole that led Bekenstein to conclude that black holes must have entropy. But he went even further. He realized that it was not only that black holes have entropy, but that nowhere in the universe contains more entropy than the surface of a black hole. And from Shannon's perspective, this can be expressed differently. More shocking still, nowhere in the universe contains more information than the surface of a black hole. To quantify this discovery, Bekenstein had to use a special system of units, the Planck units, proposed by Max Planck, the father of quantum mechanics. These units define the scale at which quantum effects become completely dominant. To construct them, Planck combined the most fundamental constants of nature, the speed of light, the gravitational constant, Planck's constant, and other related quantities. From that, he defined units for time, mass, and most importantly for this story, length. The Planck length is defined by the square root of Planck's constant times the gravitational constant, divided by the speed of light cubed. Its value is approximately 1 sextroph, 10⁻⁻⁰ meters. It is a distance so small it defies imagination, a scale at which familiar concepts of space, geometry, and even dimensionality may lose their classical meaning. And it is from here that the door to the boldest ideas about information, black holes, and the number of dimensions in the universe begins to open. Planck calculated that the Planck length represents the smallest distance with physical meaning, the boundary where quantum mechanics collides head-on with gravity, and all our familiar concepts of space-time begin to dissolve into what physicists call quantum foam. On this extreme scale, Jacob Bekenstein made a bold leap in 1989, He used the Planck length to investigate an apparently impossible question: how much quantum information can a region of space contain at most? And he found that there is an absolute limit, an entropy ceiling that no physical system can exceed. What was astonishing was this black hole's reach that limit exactly. The entropy of a black hole, or in other words, the amount of information it contains, is proportional precisely to its surface area, the area of the event horizon, not to the volume inside. Even stranger, Bekenstein noticed that each bit of information added to a black hole seems to increase its surface area by exactly 1 unit of Planck area, the square of the Planck length. No more, no less. Black holes, therefore, are objects that contain the maximum possible entropy for a given volume, and when information is added, only their surface grows, while volume plays no role at all. And then the picture widened further. It is not only black holes. It turns out the maximum total entropy of any region of space also grows with the surface area of that region, not with its volume. Black holes are simply the structures that reach the highest limit of this rule. Entropy, and therefore information, seems to care more about 2 dimensions than 3. This is Denis Gabor's idea of holography, but pushed to an entirely different level. No longer merely encoding a 3-dimensional image onto a 2-dimensional film with light, but the entire information content and entropy of the universe being encoded on the surface structure of spacetime itself. From here arises a bold, perhaps reckless hypothesis. Perhaps black holes themselves are holograms. Perhaps they do not exist in more dimensions than we think. But the opposite fewer. Perhaps a black hole is not a 3-dimensional object with a mysterious inside, but simply a 2-dimensional surface, enclosing no volume at all, only surface, and nothing behind it. If this view is correct, it suggests a way out of the black hole information paradox. If a black hole is truly only a surface, then nothing truly falls inside, because there is no inside to fall into. All matter, all information is stored on the event horizon, because that is all that exists. When the black hole emits Hawking radiation, it does so from that very surface. In this picture, both Bekenstein and Hawking are right, but not completely. A black hole must have hair, that is, it must retain information on its surface. And Hawking radiation cannot be purely blackbody radiation. It must carry information away in an extraordinarily subtle way, through quantum entanglement. Gradually, a new portrait emerges. Black holes are not merely extreme celestial bodies, like stars or planets. They may be emergent phenomena, operating at a deeper layer of quantum physics, but appearing in our universe in the form of simple 3-dimensional objects. And because black holes are places where pure gravity dominates geometric punctures in the very fabric of spacetime, what they reveal does not apply only to them, but to the entire universe. If surface matters more than volume, if information lives on the boundary, not in the interior, then what does that say about the deepest nature of reality? There is only one way to know. Keep going. In Lovecraft's story, Walter Gilman's journey ends in tragedy. After wandering through countless strange dimensions and confronting unnameable entities, he ultimately pays with his life. Gilman's death is not described in detail. We only know that something hollowed him out from within. Gilman knew he was venturing into dangerous realms, but he could not resist the pull of the unknown. Dreams dragged him out of our universe, into regions the human mind is not equipped to understand. And indeed, when we follow the laws of physics to the edge of knowledge, the consequences that appear can become overwhelming, terrifyingly so. Perhaps that is why Juan Maldacena, one of the most important minds in modern theoretical physics, prefers workspaces of absolute minimalism. A desk, a chair, a chalkboard, perhaps a window to let in light and a gentle breeze. No posters, no decorations, no cluttered papers. Only quiet somewhere the mind can escape noise and the imagination can operate freely. Curiosity and intellectual challenge. Maldacena once said, are the most important motivations, the desire to discover the unknown, and to go farther than others have gone. Born in Argentina, Maldacena revealed extraordinary talent early, went on to Harvard University, and then joined the Institute for Advanced Study in Princeton at the age of 33, a sanctuary of theoretical physics, with no students, only the best minds in the world. From the earliest days, when Einstein and Oppenheimer walked its grounds, to modern figures like Ed Witten or Andre Linde, this institute has always been the center of the boldest ideas, and it is here that the story of black holes, information, and the number of dimensions in the universe is about to enter a new chapter, one even stranger than Lovecraft's dreams. That Juan Maldacena would be chosen as the center of this turning point seems almost inevitable. In 1997, Maldacena published a paper that immediately shook both theoretical physics and pure mathematics. Since then, this work has been cited more than 20 times, becoming one of the most referenced papers in the history of modern physics. But more important than the numbers, Maldacena did not merely find a key, he opened a door into an entirely new region of reality, a region where not only black holes, but the entire universe, everything we know, everything we love, everything we can see and touch may be only a faint projection of a deeper two-dimensional reality. Of course, this discovery did not appear in a vacuum. Before Maldacena, physicists had been quietly approaching that precipice. After Bekenstein showed that black holes contain the maximum possible entropy and that their surface area increases in proportion to the amount of encoded information, many began to suspect this was not a feature unique to black holes. In the early 1992, Gerard Hooft, the Dutch theoretical physicist and later Nobel laureate, proposed a bold idea. The entire universe might be a hologram. Not long after, in 1995, Leonard Susskind pushed that idea even further in a paper with a title so blunt it was shocking, The World as a Hologram. The argument behind this intellectual leap was clear. Black holes do not only teach us about black holes, they are structures of pure gravity, and therefore the best natural laboratory we have to probe the deepest nature of that force, from relativity. Einstein taught us that gravity is not a force in the usual sense, but the result of the curvature and warping of spacetime. Matter and energy curve the spacetime around them, and that curvature determines how other objects move, from the arc of a ball thrown into the air to the formation and evolution of galaxies. Every story about gravity is a story about the geometry of spacetime. But if our understanding of gravity must be quantized, then the whole picture changes. A quantum theory of gravity would not only change the concept of force, it would force us to reconsider the nature of space and time. And space and time are not merely mathematical tools. In a very deep sense, they are the universe itself, while matter and energy are merely things that exist within that background. So when black holes reveal to us how gravity behaves at the extreme, they simultaneously reveal how the universe is constructed at the deepest level. So what, ultimately, are black holes trying to tell us first? They show that gravity and information seem to care more about surface than volume. But until then, this was still only a clue, not yet a complete theory. And it is precisely at this point that Maldacena steps in. Among the candidates for a quantum theory of gravity, string theory is the name mentioned most often. The core idea of string theory is that matter is not made of dimensionless point particles, but of extremely tiny strings, with lengths on the order of the Planck length. These strings vibrate, and different patterns of vibration produce different particles like musical notes arising from the same violin string. Most enticing of all is this: in those vibrational states, string theory naturally produces the graviton, the particle that carries the gravitational force in the language of quantum mechanics. This is why string theory was once seen as the royal road to a theory of quantum gravity. But string theory also carries serious problems. First, for strings to vibrate in enough ways to reproduce the rich particle world we observe. Space cannot have only 3 dimensions. The earliest versions of string theory required 26 dimensions, while more modern versions still need 10 or 11 dimensions of spacetime. The second problem is even more daunting. No one has turned string theory into a complete, testable physical theory. After more than half a century of research, we still do not know how the extra dimensions curl up, what their shapes are, how they affect string vibrations, and how all of that connects to the space-time we experience. These questions remain open to this day. But in 1997, Maldacena saw a decisive clue. And that clue did not lie in particles, and did not lie in strings. It lay in the holographic nature of black holes. From this, an idea would gradually take shape. Perhaps our entire universe, like a black hole, is also only a hologram, a higher dimensional reality, perfectly encoded on a boundary of lower dimensionality. And if that is true, then everything we believe is inside the universe may be only the shadow of a deeper structure, sitting on the edge of reality itself, inspired by the haunting relationship between the amount of information contained in a black hole and its surface area. Juan Maldacena began testing holographic ideas inside string theory itself. And it was here that he reached one of the most profound discoveries of modern physics, the ADS CFT correspondence. ADS is short for anti-de Sitter space, a hypothetical model universe that is extraordinarily useful mathematically. It is a space-time completely empty of matter, but with a negative cosmological constant. It does not resemble our real universe, but it has special geometric properties that make it an ideal laboratory for theorists. CFT is conformal field theory, a special kind of quantum field theory in which the laws remain unchanged when we zoom in or zoom out in space. This is a class of theories that has been studied very deeply, with many powerful mathematical tools and that can actually be solved. What Maldacena found was astonishing. When he considered a 5-dimensional anti-de Sitter space, instead of trying to solve string theory inside that 5-dimensional volume, a task that is nearly impossible, he realized that if you project the entire physical system onto its 4-dimensional boundary, the tangled equations transform into a well-defined field theory that can be handled. In other words, perhaps string theory is hard not because it is wrong, but because we are looking in the wrong place. If the universe truly has a holographic nature, as Bekenstein suggested through black holes, then obsessively analyzing the 3-dimensional volume may be the wrong approach from the start. Perhaps what matters is not the inside, but the boundary, and there on a lower dimensional space, string theory's intractable equations may become quantum problems that are difficult, but not hopeless. Nearly 20 years after its publication, the ADS CFT correspondence remains the central foundation of the entire holographic program in theoretical physics. However, the story is not finished. To this day, CFT has not been proven rigorously in mathematics, and more importantly, no one knows for sure whether this beautiful correspondence applies to the real universe. We live in a universe that seems not to be anti-de Sitter, but closer to a space with a positive cosmological constant. Even so, physicists have not stopped. In fact, much of modern research in string theory no longer focuses on string theory itself, but on the consequences, extensions, and variations of ADS CFT. The idea is too seductive. For the first time, we have a clear bridge connecting the physics of the unknown to physics that has been tested. For the first time, a serious link has been established between string theory and quantum field theory, two fields that once existed like separate continents, and so a chain of thought stretching more than 2 centuries appears before us. Carnot, with steam engines; Clausius, with entropy; Boltzmann, with microscopic statistics; Shannon, with information; Geber, with holography; Bekenstein, with black hole entropy; and finally, Maldacena, with a door into a holographic universe. A winding path, beginning in mechanical engineering and ending at the deepest nature of reality. Now, we are standing on the edge of knowledge. Behind us lie centuries of discovery into nature's hidden realms. Ahead is a veil we do not yet know whether we can lift. We do not yet know whether the universe is truly a hologram. We do not yet know whether information is the fundamental unit of reality. We do not yet know the deep connection between gravity, thermodynamics, and spacetime. But if these ideas are correct, if the universe truly has a holographic nature, then their consequences would be profound. Ironically, that would not lead to the Victorian dream of a mystical, sacred fourth dimension overflowing with spirituality. On the contrary, it would shrink the universe. It would say that reality, at its deepest level, may be only two-dimensional, and the entire three-dimensional world we experience would be only an illusion arising from a more subtle boundary structure. In that scenario, everything you, me, the stars, the galaxies lives on that boundary. Like the beings in Lovecraft's stories, we would never directly sense the full complexity of the underlying layer of quantum information. It would be too alien to the evolutionary experience that shaped our brains. Of course, not everyone agrees. Despite the allure of holographic theory, nothing has been decisively proven after decades of research. We still have not solved string theory. We still have not proven CFT. And black holes still keep their mystery. On top of that, the Large Hadron Collider LHC has not found evidence for supersymmetry, a key pillar of string theory. And if string theory wobbles, then the entire holographic program is called into question. Perhaps a steam engine is simply a steam engine. Perhaps black holes only happen to resemble thermodynamic systems. Or perhaps we have misunderstood entropy, misunderstood the nature of quantum information, and misunderstood the road we are on. So is this a warning or an invitation? What is the universe trying to tell us? If we keep going, will we find new clues, or will we only bind ourselves tighter in intellectual knots of our own making? Beyond what the human mind can comprehend, there is only one way to know. You have just followed the complete history of the universe. Don't forget to leave a comment, subscribe to the channel, and share your thoughts. Thank you for listening, and I'll see you next time.